Now let's look at a sample problem. We've got the distance the crest of a wave moves is 2 meters in 0.2 seconds, calculating the speed of the wave. So we're going to use that v equals the displacement over the time interval equation, or velocity equals the change in your position divided by the change in time. Our displacement is given as 2 meters. The total time was 0.2 seconds. Divide those two and you get 10. Not too bad. The distance from one crest of a periodic wave to the next is the wavelength. The number of crests that go by every second is the frequency. Just imagine if you saw 5 crests go by in 1 second. You measure the distance between the crests to be 2 meters. The speed is 5 crests per second times 2 meters per crest equals 10 meters per second. So the speed can also be found by multiplying the wavelength and the frequency. Or in the equation, v equals f times lambda, where lambda is the wavelength and f is your frequency and v is speed. The next sample problem, determine the speed of a transverse wave with a frequency of 4 hertz and a wavelength of 0.75 meters and an amplitude of 1.5 meters. Again, we can multiply the frequency by the wavelength to calculate the speed. So v equals f lambda, where f is 4 hertz and lambda is 0.75 meters. Notice in the problem it tells us just before that the wavelength is 0.75. Problems aren't always going to be this direct, but if they are, we like it and we take it and we perform the simple calculations to get 3 meters per second. Notice that cycles is used, so there is a unit in the numerator for cycles per second, but it is not used when there is a measurable unit in the numerator. 3 meters per second, because we don't need the number of cycles. Here are some sample problems for superposition. Looking at the first one, where we have rectangles where the amplitude is 2 centimeters and the wavelength is 1 centimeter, and it's going to collide with the same measurements, wavelength of 1 centimeter and an amplitude of 2 centimeters, but they're going in opposite directions. So these waves are in phase with each other. They're going to be at the same place at the same time. So when they collide, we're going to add the amplitudes together. The wavelength is not changed, and we get this giant rectangle of 4 centimeters high. 2 centimeters here, plus 2 centimeters here. They just add up to make a bigger rectangle. After the collision, this wave on the right is going to continue moving and is now on the left, and this wave that started on the left is now going to continue moving and is on the right. So they just pass right on through each other. The next one, we have a square 1 by 1, and another square 1 by 1 again, but this time they are exactly out of phase. So when these two are going to pass through each other, they will cancel each other out, and the total amplitude during that brief time interval is going to be 0. It's just going to be a flat line. Try this triangle. Hopefully you got something that's going to look similar to this, where it's just going to be 1 by 1, because you're going to subtract this from this because these waves are out of phase. So, what do you think now? How does water move to make a wave? Water molecules are loosely bound to one another, and when one is pulled upward, it exerts a force on its neighbors, pulling them upward as well. Notice the orange circle, that's a lot larger, but the water molecules below it are moving in a smaller circular pattern. After the water molecules have reached their peak, the force of gravity is going to pull them back down toward their position of rest. The inertia of the molecules cause them to overshoot their position at rest, creating the trough. Eventually, the upward force of the neighboring molecules and the water below overcomes the inertia, reversing the direction and repeating the process that raised the crest. A tsunami begins when an earthquake shifts the ocean bottom and creates a small step in the height of the water surface. This step is usually only a few tens of centimeters high. The small disturbance in the surface spreads out in circular waves from the point above the earthquake. That's the epicenter. But the amplitude remains small as long as the water depth does not change. However, when the wave reaches more shallow water, the wave speed drops, and the back of the wave overruns the front of the wave, increasing the amplitude just as if the waves were piling up on top of each other. This is exactly the same effect, but on a much larger scale that creates breaking waves at ocean beaches. It's the large amplitude wave that causes devastation as it hits the shore. The breaking of the waves is an example of the violation of principle of superposition. Technically, the breaking of waves is a nonlinear effect. Simple superposition is only going to apply when the waves are linear and the amplitudes are not too large. That's it. Water molecules go up. Gravity pulls them back down. If the back of the wave is leading forward, then we start to see them fall down and curl on top of each other. If you consider the center of mass of the wave on the left, if the water particles are either to the right or to the left of the center of mass, then they're going to fall over, which is what you're seeing on the left side of your screen.